Assalamu alaikum, dear students. Let's continue our last lecture. We will discuss the remaining applications of lithium aluminium hydride as a good reducing agent. Let's start with the reduction of the carboxylic acids and their derivatives. We know that these carboxylic acids are those compounds that contain carboxylic group. They may be aliphatic, aromatic, or cyclic. Upon reduction with lithium aluminium hydride, they are reduced into alcohol. You see, this carbon, it was C double bond OH, carboxylic group. So this carbon is reduced into an alcohol. Reaction with the carboxylic acid and lithium aluminium hydride is not a useful method of reduction. Why? Actually, during this reduction, what happens, we know that the lithium aluminium hydride is a good source of hydride ion. Good source of the hydride ion. And the carboxylic groups, they are the source of hydrogen ion because they are acids. So what happens, that this hydride ion, it attacks, instead of attacking on this carbonyl carbon, which is although electrophilic, but since the hydrogen, the hydride ion of the lithium aluminum hydride, it attacks on this hydrogen, so it plucks this hydrogen from it, so you get hydrogen gas. Hydrogen gas is given off during this reaction. So this hydrogen, when it releases, it may capture the fire. So when the amount of the hydrogen ion increases certain amount, so it may get exploded. So that's why this is not a useful way of reducing the carboxylic group. However, reduction may occur, but what is the mechanism of this reduction? Although this is not a good choice, but during the reaction, if there is no other choice, you'll have to employ lithium aluminum hydride. For example, a compound that may contain ketones, nitro, carboxylic group, and you will have to use lithium aluminum hydride for the reduction of all those compounds. Then definitely you will not be concerned with the yield, with the amount of the product. You just need to reduce all the functionalities. So then it carboxylic group reduces into alcohol. Let's see how this occurs mechanism. So in the first step, lithium aluminium hydride, instead of attacking at the carbonyl carbon of the carboxylic group, it attacks here. Oxygen gets negative charge, hydrogen leaves the system, and you get aluminium hydride. And I have told many times that it acts as a Lewis acid. It has an empty pocket of 2 pz orbitals, so it has tendency to accept a pair of electrons into it. So what happened here? Lithium is attached. We are using lithium aluminium hydride, so this is balanced by the counter ion of the lithium. This attacks on here, you get positive charge of the oxygen, AlH3 negative charge. When the negative charge come back to make a double bond here, then this bond moves over here, so you get RCH2CO AlH3 negative and C double bond O, and this negative charge is balanced by lithium ion. In the next step, I'm drawing the previous structure again. Another molecule of the lithium aluminium hydride, it attacks here, and this group it leaves, so you get R seed and aldehyde, and you know that these aldehydes are very reactive, so reaction occurs further. I'm not writing the more steps that I have already explained, that how ketones and aldehyde react with lithium aluminium hydride. So again, lithium aluminium hydride, it reacts, and finally you get this alcohol. So alcohol may be produced, may be synthesized from carboxylic, but from the reduction of the carboxylic acids using lithium aluminium hydride, but this is not a good choice. So what is a good choice? Good choice is that you should first convert these carboxylic acids into an ester by reacting with alcohols. When alcohol react with carboxylic acid, what you get? You get an ester. Here H and here OH react, and water leaves the system, and R is attached to this oxygen. So what you get? An ester. Now esters react rapidly with the lithium aluminium hydride, and finally you get the alcohol. Last time I told you that how amides reacts with the lithium aluminium hydride, whether the amides are primary or secondary or tertiary. So I have already explained you, because today we are going to learn the reduction of carboxylic acids and their derivatives. So in derivatives we have learned the reduction of amides. Now we will also study how esters and acid halide reacts. Reduction of acid halide an ester and anhydrides. Let's start with the esters. So when lithium aluminium hydride in the presence of non-polar solvent, so what happens in the first step, it as a nucleophile, this hydride ion attacks at this carbonyl carbon, which is electron deficient. The pi electron density moves on the oxygen. Oxygen gets negative charge, which makes a new bond with this aluminium hydride. And then hydrogen here. Then what happens when it comes back? This is a very good leaving group. Alkoxides are good leaving group. You get this compound, then what happens? Another molecules of the lithium aluminium hydride, it attacks here. This bond moves again over here. Previously it got positive charge. When this lone pair comes back, making a new bond within carbon oxygen, then this oxygen gets positive charge. So then you get this one. Finally, hydrolysis is performed, and after hydrolysis you get alcohol. You see? So in the similar way, halide could also react in the same way. First, the hydride ion would act as a nucleophile. This bond will move on the oxygen, may be balanced with lithium ion. Then again, after hydrolysis, you will finally get the alcohol. So I'm not drawing the mechanism of the acid halide. You should try by yourself. That acid halide, upon reaction with lithium aluminium hydride, they are also converted into alcohol. Now we see anhydrides. So how anhydrides react with lithium aluminum hydride? Simply, each part of the anhydride is reduced into alcohol. So you will get, since the two sides are identical, so you will get 2 molecules, 2 moles of the alcohol. Let's take a typical example. This is an acid anhydride. So when it is reacted with lithium aluminum hydride in THF, what happens? How could you predict the reduction? You just need to reduce the every part around this oxygen. So this is, it would be converted into propanol, and this part will be converted into ethanol. Okay, so in this way the acids and their derivatives react. Now we discuss the reduction of nitro compounds. So remember students, the cyclic nitro compounds or nitroalkanes react with lithium aluminium hydride and they are reduced into amines. Let's take an typical example: nitrocyclohexane. Upon reaction with lithium aluminum hydride in THF, how would they react? Simply the nitro compounds would change into amines, so cyclohexylamine would be produced. But there is exception with the aromatic amines. If you take these aromatic amines or aromatic nitro compounds, upon reaction with lithium aluminum hydride, we were expecting that this nitro group will be reduced into amino group. But what happened? It changes into azo compound. So it means that the reduction of the aromatic nitro compound using lithium aluminum hydride is also not a good choice. So what is a good choice? Remember that we will study in detail that whenever zinc metal is dissolved in acid or tin HCl in highly acidic hydrochloric acid, they reduce these aromatic nitro compounds into aromatic amines. This is whole our one lecture. We will study the detailed mechanism that how aromatic nitro compound are reduced into aromatic amines using metal acid. When metal is dissolved in an acid, then you will see that there is the electron shift mechanism. So electrons, because the metals they are the good source of the electrons, they releases the electron into the acidic medium, and those electron reduces this nitro compounds, aromatic nitro compound. So whenever aromatic nitro compounds are reacted with lithium aluminum hydride, instead of reduction of nitro compound into amine, you get the aromatic azo compounds. So in your exam, if I give you this reaction, that you should remember that this aromatic nitro compound are not reduced into aromatic amine using this lithium aluminum hydride. Instead, if the nitroalkanes or nitrocycloalkanes react with lithium aluminum hydride, they are changed into amines. Now reduction of nitriles using lithium aluminium hydride. Nitriles react with lithium aluminum hydride in nonpolar solvent, and they are also changed into amines. For example, if you take this acetonitrile and you react with lithium aluminum hydride, then you will get this product. Now question arises that how this transformation of cyanide group into amines occurs. Let's discuss the mechanism. This carbon triple bond nitrogen, it is also a polar group, and this carbon it bears partial positive and this nitrogen bears partial negative charge. So what happens that this hydride ion it acts as a nucleophile and attacks at this electrophilic center. This bond moves on the nitrogen. Nitrogen will get negative charge, and this negatively charged nitrogen it will attack on lithium aluminum, it will attack on aluminium hydride. So you will get this adduct. In the next step, another molecule of the lithium aluminum hydride it attacks here, and this nitrogen charge nitrogen will get the negative charge. So you get this two hydrogen attached to the carbon. Nitrogen is going to have this negative charge. You will get this intermediate, and this intermediate is very short-lived intermediate. After that you perform the hydrolysis. The first this nitrogen will attack on this hydrogen. You get NH, Al, H3, lithium, followed by hydrolysis. This bond breaks here and this bond also breaks from here, and finally you get amines along with formation of aluminium hydride. And since I'm throughout in all reactions you have seen that I have just reacted the one molecule of the lithium aluminum hydride with the reduction of the organic functionalities. However, this is very powerful reducing agent. It has 4 hydrogen ion that could be easily uh, donated to the for the reduction. So you see that when we will use the 1 mole of lithium aluminum hydride, you will get 4 reduced moles of the starting organic compound. Now we'll study the reduction of Oximes. What are oximes? So when ketones react with hydroxylamine, you get carbon double bond nitrogen OH compounds. These are called oximes. So whenever oxime reacts with lithium, aluminium, hydride, they are also reduced into amines. So if in your exam, if someone asks you to convert a certain ketone into amine, then simply you will have to perform the oximation. You will have to first prepare the oxime, and then this oxime can be reduced to amine using lithium aluminium hydride. If you have aromatic azides, reduction of azides. What are azides? Azides are those organic compounds that contain this azide group. This is azide group. This nitrogen gets negative charge. This is an azide group. So whenever the alkyl azide react with lithium aluminium hydride, then again this complete group which changes into amine. For the reduction of these oximes into amines, or the reduction of this azide into amine, it follows the similar type of mechanism, that this hydride attacks on this nitrogen, this bonds moves over here, and nitrogen gas, it leaves the system, and finally you will get this amine. Similarly, for reduction of this oxime, the hydride ion will attack on this olefinic, or this electron deficient carbon, and this bond will move now of the nitrogen. After the hydrolysis, you will finally get the cyclohexyl amine. Now in the last, I am describing here a very good example that how this lithium aluminum hydride could selectively reduce a certain functionalities. So this compound, it contains two functionalities. It's an ester, it is also contain ketonic group. So lithium aluminium hydride in THF. So if I use this reducing agent, then we know that the ketone, it will reduce ketone as well as ester into corresponding alcohols. Now I'm not writing the mechanism, you will have to practice it by yourself, that when you will react this compound containing, which is bifunctional compound, you will get this product, both group will be reduced into alcohols. If you will use sodium borohydride in methanol, as a reducing agent, you know, it it does not have a tendency to reduce the ester. It will reduce this alcohol, this ketone into alcohol. You will get this product. So this reagent is the chemoselective reagent. What is chemoselectivity? Chemoselectivity occurs when you have two or more than two functional groups, and a reagent selectively reduces one functionality, then this is called chemoselectivity. So in the presence of other functionalities, only one of the functional group is reduced. So this is called a chemoselective reaction. Sodium borohydride is a chemoselective reagent. Now why ketones are reduced and esters are not? You will have to recall the lectures where I have used this reduction with sodium borohydride. You see that the ketones and aldehydes are more reactive. Here the carbon is much more electron deficient as compared to the carbon present in the ester. Why? Because the oxygen that is attached with this carbonyl group, it it actually reduces the electrophilicity of this carbon by donating a pair of electrons. So that's why this group is not as much reactive, not as much electron deficient as compared to ketone. So sodium borohydride, which is a mild reducing agent, it could only reduce this keto group, not the ester. Now the question is, how will we convert this compound into this one? Which reducing agent would be used? When you will use lithium aluminium hydride, it would reduce both the functionalities. If you will use sodium borohydride, then it will selectively reduce ketone but not the ester. But here in this conversion, you will have to reduce the ester in the presence of a ketone group, which should remain intact. Think over it, search from the internet, and then find the answer. This is very important examples. So so in this lecture, which was quite big lecture, we covered initially the structure of lithium aluminum hydride. We also learned that what are the functionalities it can reduce and what are the functionalities where it is resistant towards the reduction. It does not offer the reduction reaction. So only the non-polar bonds like alkenes, acetylenes, and which are very much isolated, they does not react with lithium aluminum hydride. However, if they are a part of the conjugation, like in the cinnamaldehyde or the cinnamic acid, they would also get reduced. Then we learned the reduction of ketones, aldehydes. We also studied the stereochemistry of this reaction. That when we studied the certain examples of the cyclohexanone, where the 4 position was substituted with a bigger tertiary group. So how, where, and how lithium aluminum hydride reduce that alcohol. We also studied the reduction of amino acids. We also studied the reduction of esters, aromatic nitro compounds, cyanides, nitroalkanes, and also we studied the reduction of oximes and azides, etc. So students, you should cover this complete lecture from different books. You will and solve the examples by yourself. Here I have written few examples for you, so you should solve all this problem by yourself. I hope when you will understand this lecture, then this problem would be quite easier for you. So good luck. Allah Hafiz.